Okay. Okay. So topic of today is Fourier transform. So there are many ways the Fourier transform shows up in mathematics. So let me recall an instance of this first. So let's fix a finite field characteristic P at Q. And let us also fix psi from K to say QL bar cross, non-trivial additive character of K. So here I could just choose a field of complex numbers, but later on I will need to make such a choice, so I do it right now. And you have, if V is a finite dimensional vector space, and you have a function. So in particular, V is just a finite set. You have a function from V to R. Then its Fourier transform is defined as follows. So f psi of f. So it will be a function on the k linear dual of V. Again, and it sends y, the sum over all x in V of f of x psi evaluated on the pairing of x and y. Okay, so this is an element of K on which I can apply this additive character psi, which plays a role in this finite field setting of the exponential of 2 pi I that is used when you define in real or complex analysis the Fourier transform for the first time. Okay, so what I want to do first is to explain how to geometrize this. V is finite. Yeah.
Sorry.
But I have no eraser. This is well defined and satisfies the usual properties of Fourier transform. It's anti-involutive, etc. And so geometrization of this finite field Fourier transform was done by, like, geometric analog was first discovered by Deligne, and then the theory was developed by Laumon in the 80s. So let S be a scheme, or more generally, can even be a stack over my finite field K as a row. And let V over S be a vector bundle, the geometric vector bundle, with dual I just mean geometric realization, the total space of the vector of the finite locally free. And I will fix psi as a goal. It gives rise to a least sheaf L psi on the affine line. Okay. Therefore, also by pullback over S. This comes from the fact that you have this Artin-Schreier map on A1, which is a finite étal Galois cover with Galois group, exactly the k rational points of A1, which are just k. All right. And then you can look at the following diagram. So you have V dual and V. They both live over S. And then I consider the fiber product over S of the two. So because these are dual vector bundles, there is natural pairing to A1 over S. And let me call this alpha, and this will be called pi and pi dual. And the geometric Fourier transform is defined as a, so it's attached to this choice of psi and to the data of this vector bundle V. So it will be a functor from the bounded constructible category of l-adic sheaves on V towards bounded constructible category of l-adic sheaves of the dual. What you do is that if you have an object here, so it lives over V, you pull it back along the morphism pi and tensor it by the pullback of this Artin-Schreier sheaf on the affine line, and then you push forward along the other line. First pullback along pi, tensor with the pullback of the Artin-Schreier sheaf. And then push forward. So all the functors are understood to be derived. Okay, so this is this geometric Fourier transform. So why does it deserve this name? Well, if you take remark that if you take G to be just the trivial V is a finite dimensional K vector space as before, and you just take V to be the associated trivial vector bundle. And if you take A to be an l-adic sheaf on complex of l-adic sheaves on V, then as I explained in my first lecture, you can attach to A function on the set of k rational points of V. And so the claim is that, so I denote it like this by taking trace of Frobenius on the Stokes at k rational points. And the claim is that if you compute, if you take this geometric Fourier transform, f psi, and apply it to A, so when V is fixed, I will also sometimes just denoted like this. So I take the geometric Fourier transform of A, and then so this gives me a complex of l-adic sheaves on V dual. So I take the associated Frobenius trace function, and this is just what you obtain by applying this function theoretic Fourier transform to the trace. This is not completely formal because you need to see at the level of trace function how these various functors act. And for this one, for example, you need to Lefschetz, Grothendieck-Lefschetz trace formula, but this is something you can prove. And this is in this sense that this functor defined on category of l-adic sheaves geometrizes this naive Fourier transform. So something that Laumon proved. Well, so this geometric Fourier transform has nice properties which are same kind of properties as the usual Fourier transform has. So first of all, the formulation of this Fourier transform commutes with base change in S. one has a natural isomorphism between. So let's say I first apply V is fixed. So let's say I first apply the Fourier transform for V, and then I compose it with the Fourier transform for the dual vector bundle, still with the same character psi. So now this one goes from p-adic sheaves on V dual to p-adic sheaves on the double dual. And then the claim is that this is equivalent to push forward along A, where A is minus the canonical identification, the canonical isomorphism between V and its double dual. Okay, so the Fourier transform is not involutive. There is still this minus sign, so it's almost involutive. And in particular, it produces an equivalence of categories. Between this category of sheets on V and the category of and one last property, which is slightly unexpected, is that it also commutes with Verdier duality. So that's a bit unexpected because Verdier duality would exchange lower Schritt and lower star, and this morphism is pi dual is not proper, so fine. But the content of this claim is that in fact I could also have defined the Fourier transform with using pi dual lower star instead of pi dual lower Schritt, and this would have given me the same thing. So this has nice property. For example, this implies that Fourier transform preserves perversity, because I mean, once you have this commutation with Verdier duality, you only need to check that it is, okay, I never know which one, right or left exact, and this then follows from the fact that you are pushing forward along some affine morphism.
So it's the same lower star instead of lower Schritt to mean up to a shift by the dimension or twice the dimension?
Yes, I guess probably. Yes, yeah. And here as well, I guess the statement is probably up to shift. In general, one renormalizes this Fourier transform by shifting by the dimension of the bundle. I will just ignore all the shifts in this lecture. So this Fourier transform found many interesting arithmetic applications by Deligne, and Laumon, and Katz, and many other people. One application I want to discuss is so going back to my first lecture. So this application is due to Laumon. So let me recall the setting from lecture 1. We had, so K was exactly as above, isomorphic to FQ. And then we had a smooth projective geometrically connected curve over K. And we also, okay, with like function field denoted by capital F. And we had fixed sigma, a representation of the absolute Galois group of F, and dimensional p-adic representation, which was, of course, continuous, but also irreducible, and most importantly, everywhere unramified. And the main theorem of lecture 1, the main claim was that to this we should be able to attach an ramified automorphic function for GLF. And what we had done in lecture 1 was we had constructed using. So I discussed, if you remember, I discussed the case where n is 2, and there the argument was based on Fourier analysis. And then I just stated without proof a more general statement due to Schalika, which, as I said, follows by exactly the same argument plus some induction on n. We had constructed a function, smooth function, f prime sigma, which was defined in DLN of the head of f modulo the maximal compact subgroup. And it was invariant on the left by Mn. Mn, I recall, was the mirabolic subgroup. So matrices of like first a block of size n-1, then 0, and 1 on the last entry on the diagram, and whatever you want above it. Valued in 12 bar. And we wanted to prove that this function is wanted. But as I said, it's impossible to check it directly. That f prime sigma is left invariant, in fact, by something bigger, namely the full, instead of just the mirabolic subgroup, GLN f itself. And I said the trick is to devise by Drinfeld and Laumon is to geometrize everything. That is, replace using the Scholze function dictionary. You want to replace functions as f prime sigma, but by Scholze, and try to reduce this invariant statement to a geometric statement. But I did not explain. How this geometrization is done, and that's what I want to do now, using this definition of the geometric Fourier transform. So for this, I will denote by let me fix some integer I, and let co I be the algebraic stack of flat shapes on my smooth projective curve X. So now the notion of flat coherent shift is the usual one from algebraic geometry. So this parameter, this is the functor which sends, sorry, I forgot, it depends on I of generic functor. So if I is 0, for example, I'm just looking at torsion coherent shifts. So this is a functor sending a K-scheme S towards the groupoid of coherent shifts on X times S, which are flat over S, and have fixed generic rank I. And inside that, I will let, I won't really go give a proper definition, but let me take Ci to be an open substack of this moduli stack of flat coherent shifts, such that if EI denotes the universal flat coherent shift on Ci, then Vi, which I find to be home from highest tensor power of the dualizing shift on X to Pi is a vector boundary. Okay, so what I mean by this notation is really like the functor. I mean, it should send T to home on like of O x or any t over ci, it should send this to. So I just want to choose some substack inside that so that this is a vector bundle. So in other words, I want to like just put some condition on the slopes so that there is no x1. Okay, and then using third duality, the dual vector bundle, VI dual, is given by is isomorphic to x1 of no, I have EI omega x times I plus 1. Okay, and so in particular, I can apply this Fourier transform diagram as before. So you have VI dual times VI. So now the base S is this stack CI. Diagram. And on the map here to A1, in terms of this description, it's just a map, natural map to x1 omega x to the I, omega x to the I plus 1, which is the same as x1 the structure shift, which is again the third duality isomorphic to A1. And in particular, I get an associated Fourier transform, which I will just write f psi I, which is the Fourier transform attached to this. Okay. So that's the first step of the construction. And in this statement of Shalika, there was this, we were using Fourier analysis plus, as I said, some inductive argument. We need to somehow start with the case when n is 2 and then increase n at each step. So this is what we can also do geometrically as follows. So I will set inside VI that VI naught is a open defined by the condition. So VI parameterizes an S point of VI is a flat coherent sheaf on XS plus a section, I mean a map from omega x to the I towards this flat coherent sheaf. And VI naught is defined by the condition that, so this pair formed by a flat coherent sheaf on a map, S, I want to put the condition that S is injective. And dually, I also want to, inside VI dual, I define VI naught to be the locus where, so no VI naught will parameterize short exact sequence like this.
Plus 1.
I plus 1, yes, thank you. And where F belongs to CI. And I want to, so this is what VI dual parameterizes. I want to add the condition that F prime also belongs to CI plus 1. Okay, simple observation is that you can see that VI dual naught is in fact isomorphic. That's for gamma I. With VI plus 1, no, Why is that? Well, okay, what is an S point of this? As I just said, it's such an extension. But in particular, the datum of such an extension is, I can also just remember this injective map. And if I have such an injective map, is exactly what defines an S point of VI plus 1 not. Conversely, since I did not give the precise definition, you have to believe me, but I think it's at least plausible that these two things are the same. Yeah. Marcus?
Sorry, why is the quotient necessarily in CI?
Yeah,
I just have the injective map.
Because I did not give the precise definition, but I mean, you have to write down the exact definition of which CI you want to consider and make sure that this property will be true.
Okay.
I'm confused about that. Like, how is it possible you have a short exact sequence like that and the generic rank doesn't just bump up by more? Like, why is this a condition at all?
I
mean, if F is locally free, such an extension is always locally free.
CI. Say it again.
Oh,
so the index is supposed to remember the generic rank.
yeah.
But this is not like co-I plus 1. This is some open inside it, which is defined by some condition on the string.
I see. Okay. Now I understand. Thank you.
But can I ask, if F is in CI, it means locally free?
No, not necessarily locally free. It can have some torsion as well.
What was the CI condition? Yeah.
I want to make sure that this thing I define here is a vector boundary. So basically, you put a condition which ensures that this x1 of omega x to the I against your flash coherent shape vanishes.
So far, I haven't seen why we should change, why we considered co-I instead of fun. Can you explain that? Because all these constructions make sense for fun as well.
Well, imagine that, for example, to have such a thing to be true, like I have here, you have an injective map between this line bundle towards a certain, let's assume it's a vector bundle. This co-kernel could have a priori torsion.
Okay.
So
yeah, it's in this this last statement.
It's an error, like you have to allow. So we want to do some inductive argument, which will actually start with the case where I is 0. So we will start with torsion coherent shifts, and ultimately, in the end, it's true that the function we want to produce, we will restrict everything to the sublocus where we have like no torsion, so a vector boundary. But the construction makes it necessary to also allow more general coherent shifts. Okay, so why am I saying this? I'm saying this because now I want to draw a bigger diagram. Sorry. So you have, okay, let me start with I being 1. So VI not is a sub of V1, and we have the Fourier. So this is open substack in core1, and now we have this Fourier diagram between V1 and V dual, and inside that we have this V1 dual knot, which, as I just said, is isomorphic by this gamma 1 to V2 knot, which itself is contained in V2, and then you can just continue. So this maps to V2 and so on. And here, V1 knot, you can also map this to 0 just by, if you have a pair F and S, where this is a generically aligned bundle, and S is a map from a dualizing shift to F. You can map this to the co-kernel. Defines you a flat coherent shift of torsion coherent shift. And therefore, what you can do is define, we get functors F psi I naught, which now go from, for each I, which now go from V at VI naught vi plus 1 not. Namely, what do you do? Well, you define it to be, so you start here, say I is 1. You start here, you first extend by 0, apply Fourier transform, restrict, and identify along gamma 1. So if I write it down, so as I said, first, maybe I should give names to this map. So Gi and Gi. Extend by 0. Apply Fourier transform. I. Restrict. And compose with isomorphism. Gamma. Okay, so that's a lot of notation, but what you should remember is that using this Fourier transform, we have no way to, we got a functor which goes from l-adic shifts on vi naught to l-adic shifts on vi naught, v naught I plus 1. So we increased the generic rank by 1. And this is the way this inductive argument is geometrically implemented. So in particular, if you compose, so if n now is some integer bigger than 1, which would be the, I just erased the statement, but for the dimension of my given Galois representation, I can define by composing we get a functor an of psi, which goes from sheaves on stack of flat coherent sheaves towards sheaves on what I call the prime n in my first lecture. So how is it obtained? Well, you start from an l-adic sheaf which lives over there, pull back to v1 naught, and then just compose these various. Okay. Let me call this part f. Right? So first you pull back along f, then you apply this f psi 1 naught, then you apply f psi 2 naught, and so on, until you get to f psi n minus 1 naught. And what do you get at this step? You get an object which lives on Vn naught. Yes, and then you just apply like restrict. For this, amount of notation where delta n is just the inclusion of one prime n. So I recall that what one prime n was, it's just open a substack inside Vn naught, where this flat coherent sheaf of generic rank n that I have is actually a vector bundle. So it's locally free. Okay, is the construction clear?
Was that the definition
behind, but that is
was that the definition of 1n prime?
So maybe I rewrite what prime n was. So we call prime n sends S K scheme to pairs Fs, where F is the rank n vector bundle. On X times S. And S was an injective map of omega X to the power n. One. So you see it's lives inside n naught. The n naught is the same thing, except that you only require that you have a coherent shift of generic rank n. Okay. So we have this attached to psi. We have defined this functor from L-adic shifts on the stack of torsion coherent shifts towards L-adic shifts on band prime N. Okay, so now there are basically like two steps in the argument. So the first one, which is in some sense, not exactly, but in some sense, it's a geometrization of this result of Kasselman-Shalikar, which I stated in the first lecture, which was telling you that you have this attached to sigma, and in fact just to the conjugacy classes of the images of Frobenius by sigma for every close point of the curve. You have these local Whittaker functions. And geometrizing this, Laumon constructs attached to certain constructible shifts equals 0 attached to L, which is a rank n local system on the curve corresponding to sigma. So sigma is everywhere unramified, so it corresponds to an L-adic representation of the pi1 étale of the curve that is correspond to a local system of rank n on my curve. And to this, Laumon is able to attach in a rather complicated way a certain object there. All I can say is that the pullback of this, how it's related to L exactly, well, it's pulled back to the symmetric product of the curve is isomorphic to the this symmetric power of L for each. And here, the map I have is that whenever you implicitly using that you have a natural map from div D to co0, simply if you have an effective divisor of degree D, you send it to the like torsion shift, which is supported. And so in particular, if you take just D to be 1, have the map sending a point of X to the skyscraper shift at this point. And if I pull back this Laumon shift on co0 to X, then I just get back this local system L I started with. Okay, and then the theorem, which is not obvious, due to Drinfeld, Fourier, Langlands, and Drinfeld, tells you that if you apply like the trace function of what you get by applying this functor A and psi to this Laumon shift is exactly this F prime sigma. Okay, so I start with the Laumon shift leading over co0. I apply this functor I just defined before using by composing Fourier transforms, and I obtain something which lives on band prime n. And so, in particular, if I take the trace of Frobenius function, as mentioned in the first lecture, I get a function leading on this double coset, where on the left I'm ordered by the parabolic. And the claim is that this is exactly the one we have constructed by hand in the first lecture. That's really not obvious, but you can check it, and this tells you that this maybe rather complicated geometric construction is the right one, and this produces the correct output. And then the rest of the argument, which I won't discuss, is the hard part. So the hard part is to prove that this object is in fact pulled back from gun n. Have a natural map from gun prime n to gun n by just forgetting this section S, and you want to prove that this thing you have here is in fact pullback of something on gun n, and so in particular, by taking the trace function of this something on gun n, you will get the desired automorphic form. But this is where you really use the geometry of the situation, and in particular use the fact that this is in fact a perverse sheaf, which is also not obvious, but at least maybe plausible from the fact that all these Fourier transforms, as I mentioned, they preserve perversity. And the object that Laumon produces here is a perverse sheaf.
One thing about this theorem, so you said there's something one checks. So is it really a direct calculation, or is it some indirect argument that this will turn out to be F prime?
Yeah, it's more or less a direct calculation in the sense that you have to follow each step of the construction and see what it does on trace functions. But the difficult part is the starting point, so where you need to analyze this construction of Laumon, and which is closely related to something called geometrization. And so you have to understand, geometrization well enough to be able to prove this statement.
But you say making explicit
this construction using some, he was calling this global Fourier theory, because he did this before geometrization was developed. And I think it's like the insight of this, for people to realize that the construction he makes is closely related to geometrization, and use this as an input to analyze the trace function.
Can you tell how many people came up with this iterated Fourier transforming this sheaf level construction?
How did he,
like, without knowing for sure that it was the correct analog of the?
Well, he was able to check things when n is 2. And like the fact that you do this iterated Fourier transform is quite reasonable if you look more closely into this the proof of the theorem of Shalika, which I did not do. I mean, I just did the case where n is 2, and then I
but
said
in case n equal 2, Laumon was able to check that.
Yes, it's in fact it's true to it's a formulation of what Drinfeld had already done. Yes, but yes, that's right. What was, as I said, the difficult part for proving this is really understanding the very first step. Then the fact that you are doing the correct thing is, I think, not so surprising.
But you didn't tell us how to construct this.
No, and I won't, because it's complicated, and it's like how it's a different topic. I want to focus on this some of the simple part of this geometrization process, which is, I mean, this involves a lot of notations, but this is not a difficult construction once you have this Fourier transform. Something else I can say is that, okay, you may be, I'm actually slightly cheating here, because all this, I mean, this object, for example, is not like defined on all of bond prime n, but only on the inverse image of in bond prime n of the locus where my rank n vector bundle lives in this open substack Cn. But in practice, it does not matter, because all these objects will construct are some Hecke eigenfunctions. At the level of sheaves, there are some kind of equivalence property for the geometric analog of equi-operators, which I did not define. And so it's like if you have some equivalent sheaf and you have it's defined on some open such that like, all the iterates of this open by the group action cover everything. So if you know it in restriction to this open, you know what it has to be everywhere else. It's like in geometric classes. Okay, very good. So that's all I wanted to say about the classical, so to say. Now I want to go back to this Fargues-Scholze setting and explain something analogous for us.
Sorry, can I ask one question nevertheless? So you say it's the hard part to prove that it's pulled back, but I mean, just very roughly, how is it done? You construct an explicit thing on ban n, and then it's hard to show that its pullback is that, or what is?
No. First of all, it's really the part where the geometry is useful, right? Because if I explain all of this, you may have the feeling that I'm just making something very complicated to just produce a sheaf with trace function I already knew how to define. So it's really, so somehow I'm skipping the part where the geometry really enters. Now the way it's done is by, as I said, using that you have a perverse sheaf and you want to prove it's constant along the fibers of this map. And first you argue that these fibers, at least when the degree is big enough, are like simply connected. So it's enough to prove that it's locally constant. So this looks like geometric class theory. So
it's a probability de ligne.
Well, yeah, but this is the part which is easy in the argument. And then the difficult part is proving this local constancy along the fibers. And you do it by using a numerical criterion due to the lean, which reduces you to check something about the Euler characteristics of the fibers. And then you can, the trick is to move the local system, to reduce to a numerical statement for which you can, like, say, move the local system in some connected component of a stack of local systems, and reduce to check descent for explicit for just one local system. And then even then you are not done yet. But
it's easier to descend reverse sheaves because that's an abelian category, so you don't have to worry about higher coherences. Is that the idea?
Well, first of all, I think for the statement to be meaningful, I really need to make it more precise. Really, that could be. I use the fact that the fibers in high enough degree are connected and smooth, and so pullback functor is fully faithful in the category of perverse sheaves. Right. So already, like, I want to make a statement which uniquely specify what the descent has to be.
That's just a condition, yeah.
But then, as I said, it's you use this theorem of the lean, which I think is really true for perverse sheaves. Good. Okay, so now let me go back to the setting of the last lecture. So again, we call E a field, this residual field Q and uniformizer fixed by phi. So what did we do last time? I explained that we can actually make sense of stack of flat coherent sheaves. Because this object was the V stack for this topology of Scholze. I mean, I gave a definition of what it means to be a flat coherent sheaves. I put it between quotation marks because it's not flat in the usual sense. So I recall it just means that locally on the relative Fargue content curve, this object can be written as a co-kernel of fiber-wise injected morphisms between vector boundaries. Okay, so coherent sheaves on and exactly as I did above, let me I is some integer bigger than 1. Let me define Ci. It will be an open substack of this B stack, where it's formed by those flat coherent sheets F on a relative half content curve, such that for every geometric point, I want to put the condition that, first of all, that if I look at the pullback of F to the half content curve over this geometric point, I want to require that Fs has generic rank I. And also, all these Ardan and slopes must be non-negative. And use a convention that something which is torsion is slope plus infinity.
Is this an open substack?
Yeah, it is actually an open substack. Yes. So actual definition needed to make all these things work well is actually slightly more complicated. So this is a little light, but basically that's the idea. And as we saw also last time, if S is any perfectoid space in characteristic P over Fq, and if I take F, which belongs on S point of this open substack Ci, because of this assumption on the slopes, which is really like a pointwise statement, we have that this forward along tau, defined last week, is in fact concentrated in degree 0. Tau was this. So basically, it's so this is a functor which sends T over S to the homology on the curve associated to T of F. And I said that this is actually a V sheaf. And because of the assumption I put on the slopes, it's supported just concentrated in degree 0. There is no higher homology. And this is what we denoted like last time, like BC of F. The Banach-Colmez space attached to this. And what I did before with vector bundles, I want to do the same now with Banach-Colmez spaces. So namely, I want to define the Fourier transform for Banach-Colmez spaces. And well, to give it a meaning, I need to tell you what the dual of such an object is, and then I need to tell you what p-adic sheaves on such objects look like. After I have done this, I can just copy the definition with this diagram to define the Fourier transform. So this will be on spaces over S. It's always even, I mean, we saw it at the very end, it's even the diamond. So some kind of algebraic space in this Fourier world. So first, let me define the dual. So to do it, it's technically convenient to, I mean, the way we do it with Anschütz is using the language of Picard stats. So next week I will discuss examples, and it will be maybe more clear why it's useful to use this more general formulation. So this BC of F, as I just said, is a V sheaf of P underline modules. I can see this as a subcategory of what we call Picard stacks in E-vector spaces, which is roughly speaking, it's just a Picard stack for the V topology with an action of E underline. The way to think about this category is it's by the statement which is due to the line without the E action, but which you can generalize here. This is the same as, yes?
Sorry, what is this the dual of?
I want to define the dual of such a BC space. V sheaves of underlying E modules, which have only cohomology in degree -1 and 0. The functors I can denote them. As I said, this is basically due to the notation is not optimal, but the functor in this direction will denote. This has nothing to do with tilting, so that's maybe not. I mean, that's apparently standard notation. I hope this will create no confusion. I mean, what does this complex look like? Well, basically, its cohomology in degree 0 is just a set of isomorphism classes of objects of the corresponding Picard stack by the sheaf of automorphism of the unit object. So, for example, two simple examples to keep in mind.
H minus 1.
H minus 1, thank you. Two examples to keep in mind is just like if G is just the V sheaf A, then so like no automorphisms. So if it belongs to this subcategory here, then the associated complex is really just A in degree 0. Whereas if G is classifying stack of A for A as above, then the corresponding complex is just A puts in degree chronological degree -1. So if you have such a given G, such a Picard stack in E-vector spaces, you define its dual to be internal home in this category of G against the classifying stack of E underline. So in this category. So if you prefer to think in terms of complexes, the complex attached to the dual is what you get by you take R home in the category of this category of sheaves of underlying E modules on S. So everything is on the ambient category is perf S. You take R home in the of G against E put in chronological degree -1. Well, this may have many higher X, so you truncate. This way. Yes, so that's the content of the next statement. Okay, so just some general formalism. So if I would have defined Ci to be the substack where the Ardan-Arasiman slopes are positive instead of just like non-negative, then I could just have worked everywhere with sheaves, and I will not have like needed this general formalism. But next time we will discuss some interesting examples where the vector bundle we take is actually the trivial bundle, and there, as we have just explained now, you get like some kind of sheet. So let me write it down. The proposition is that so if S for S in vertical space and F S point of this stack Ci, and I is just integer. You have that the natural map from DC of F towards, so seen as an object of this category, to its double dual, is in fact an isomorphism. So the objects, the BC space, Banach-Colmez spaces attached to that coherent sheaves in Ci are realizable. And you can actually describe, compute them in like basic situations. So if you say lambda is a rational number, which is not zero, so strictly positive, rather, then O of lambda defines a nice, and for any S defines an S point of Ci for appropriate I, and the dual not of this, sorry, O lambda, not very surprisingly, is just the DC of O minus lambda, which I recall, because this no is negative, is R1 of star of this negative slope vector. So yeah, you should do it twice and you just recover DC of O lambda. But it's important here that lambda is not zero. If lambda is zero, then, well, then as we saw last time, DC of O is just E underline, and the dual of E underline is now the classifying stack of okay, and this statement is a direct consequence of this follows from the results of the last talk, namely, well, the fact that we have, first of all, the fact that we have this nice, well, no, so it just follows basically from third reality, what I call third reality on the partition. Okay, so output of this, we can define for such BC spaces, we can define their duals. And if I take the double dual, I just recover the original BC space. So this is quite similar to what happened at the beginning for vector bundles. Okay. Next. To define the Fourier transform, I also need to speak about p-adic sheaves. Maybe another example I can give here is if S sharp is okay, in the definition of Ci, I assume that I is bigger than 1, but it's in fact not necessary. I can just take any non-negative I. And let me look at the case where I is 0. So let me fix an until S sharp of S. And then you remember that we have this, that BC of the skyscraper shift along the associated Cartier divisor, the relative curve, was just the diamond attached to the affine line over S sharp. In this case, the role of this is isomorphic to again A1 itself. So p-adic shifts, contrary to the scheme situation.
Can I ask you, is superscript P, why superscript P, why that notation?
I don't really know actually. I think Deline uses notation in SGA, and
Okay.
I agree that it's not. I should have changed it before the talk because no, it's like a bit confusing with the tilting notation. But yeah, I'm not exactly sure why it chooses this notation. In this paper, which is called La formule de dualité globale, where it introduces this notion. So p-adic shifts. So to speak about shifts, like you could work also with QL bar coefficients, but that's a more complicated theory. So I will just deal with the case where lambda is a torsion ring, which is killed by some integer prime t. For example, fix a prime L different from P and look at Z modulo L to the N. So Scholze was able to attach to any stack. So there is actually a little technical condition, sub-theoretic condition called smallness, which I will skip. Say y. Some lambda linear stable infinity category denoted by Z8 of y lambda, which is a full subcategory of the category of all V-shifts of lambda modules. Well, lambda is just on dot with a discrete topology on the V side of y. And a 6-1 formalism with the usual property. Base change, projection formula, the various adjunction you are used to, and so on. Of course, I don't want to get into the definitions. Let's just take this as a black box. You can just think to this as a category of shifts, of étal shifts of lambda modules on Y. Although this is not true in general, but this is at least true for a certain class of diamonds, the so-called locally spatial diamonds, which include this BC space example. In general, it's defined by V descent. So this Y goes to the head of Y lambda, this V shift, hyper V shift of infinity categories, and so it also defines everything first for strictly totally disconnected perfectoid spaces, and then defines the category in general by descent. I can maybe just remark about this general definition is that, well, maybe two remarks. That the functors, if you have F and morphism of V stacks, the functors F lower star on F upper star makes sense without any assumption on F. But F lower sheik, and thus also F upper sheik, which is defined as its right adjoint, they are defined under some condition. These conditions are there essentially to ensure some kind of finite homological dimension. So you want this, you define this, and you want to get the right adjoint, you want this to commute with direct sums, and you are in this, well, everything is left complete. So it's only reasonable if you have such an assumption on F, I believe. And of course, this is not, you don't put such a global condition on F, you want to put a local condition. So this is ensured by requiring that F is representable in a locally spatial diamonds. So, okay, diamonds, we know what they are. We discussed them last week. Locally spatial just basically means that the underlying topological space is spectral. So it looks like a speck of a ring. And plus a local condition on dimension of points. I think it's only in this, I'm not completely, I think it's only under this assumption that some of the spaces you have are spectral, that it's reasonable that, like, let's forget that we are looking at étal cohomology and imagine that you only deal with analytic cohomology. Then you want to know somehow that the cohomological dimension is bounded by something like the cool dimension. And this is something which, by the theorem of Scheidera, holds true for any spectral space, but which is, like, I guess, completely false for compact Hausdorff spaces. So the condition you put is like something which controls the cool dimension and also like the geometric transcendence degree at each point. But okay. General enough for us. Another condition, remark I want to make is that in some sense the definition in this p-adic setting is in some sense it's easier than in usual algebraic geometry because you have this. First observed by Huber, you have this notion of canonical compactification of a map. So to define F logistic, you want to, at least let's say F is quasi-compact, you'd like to write it as something proper, composed with some open immersion. And the nice thing with p-adic spaces, which is again a phenomenon related to the existence of higher round points, is that you can, in fact, do that, obtain such a factorization under some small assumption in a canonical way. Like you don't need to make a choice and then verify that everything is independent from choices you make. That's a nice feature of p-adic spaces. I think most people are familiar here with condensed mathematics. This phenomenon is already visible in the first course in condensed mathematics, in the discussion about coherent setting, where also one sees that by going from schemes to like discrete p-adic spaces, one gets very like the same mechanism applies and gives a nice way to define the lower sheik. Okay. That's all I want to say about p-adic sheik. So let's basically take it as a black box. And so now let me finally define the Fourier transform. Here as well, you need to choose some additive character. So now, psi is an additive character of E. This value is in units of lambda. Beta. So it gives rise to an object, to a sheet on this stack 1.e lambda. This stack will play the roles that affine space, the affine line was playing in the characteristic P schematic set. Namely, let me fix, let's say you have S in pair, and let me choose F flat coherent sheaf with for some given rank, say a generic rank, and more importantly, this condition on the slopes. Then you get the following with V corresponding BC space. Well, you have V dual. I just defined it. You can take the fiber product of V and V dual over S. So the situation is more completely analogous, except that this fiber product, by definition of the dual, naturally maps to classifying stack E on the line. And so to define the Fourier transform attached to this, well, you just do so it goes from d hat of V lambda to d hat of V dual lambda. And what it does, it sends A by shape rho of the fullback of A on pi cancelled with the fullback of X. What is lambda again? Lambda was my coefficient frame, which I assume to be torsion. Point to P, yes.
Okay. I'm a little bit confused about the existence of such maps psi. So, like, what example do I have in mind?
Well, I guess you don't want lambda to be finite, right?
Yeah, that's what confuses me.
Yeah, but I don't assume that lambda is finite.
Okay.
So you can just choose, I don't know, FL bar. Yeah. Yeah, I mean, it would be better to, of course, to have a theory which also works with characteristic zero coefficients, but there are some technical difficulties which have to do with this six-functor formalism. So, but of course, like a similar story should also work with lambda being something like 12 bar. Okay, so this is this Fourier transform, and well, maybe first I state the proposition, which is exactly the same as in the schematic setting. So, formation of F psi commutes with the base change in S. We also have, it's also anti-involutive, so we have natural isomorphism between psi V dual goes to V double dual and goes with psi for V. And same as before. Here, like I use the fact that this B shifts I'm considering here are satisfy this generalizability property. So in particular, it is an equivalence. It also commutes with their divergence. Unfortunately, there is no good notion of perverse shifts in this p-adic setting, so I wouldn't know. Yeah, it doesn't make sense to require whether this functors preserve perversity or not, but that would be very nice. Such a thing would exist. But at least this formal statement is true as before. And yeah, so one example, well, something I should maybe mention, maybe remark here is that compared to the compared to the previous situation, basically what we have done is that we have replaced A1 by the classifying stack of E underline. And the reason for that is, in other words, we have replaced, remember how A1 arised? In the first case, it was like this local text of OX, or where X was a classical curve, against the dualizing shift, by by the stack of extensions of O by U. Where O is the structure shift on the far content. So that's a difference, right? I mean, there is only one extension of O by O, which is just the trivial round-2 vector bundle, O plus O. But this has a non-trivial automorphism group, which is given by E underline. And you have to take it into account if you want to take to get something interesting. So this is a bit reminiscent of what we briefly discussed for geometric class field theory. So this is reminiscent of the fact that in usual geometric class field theory, so this argument of the Lie, which I gave at the end of the first lecture, we use the Picard scheme. We have this Fargues-Scholze map. We could have used Picard type or Picard scheme, but one is a GM gerb over the other, so that does not make difference as long as one speaks about p-adic shifts. And therefore, you just use a Picard scheme, and this is actually what makes the argument with the fibers of the Fargues-Scholze map work. But in Fargues, version of geometric class field theory, which was mentioned at the very end of the last lecture, I guess, one before, we really need to use the Picard style. Because the Picard scheme, so to say, is trivial. There is only, for each degree, there is only one line bundle of degree D, but it has this automorphism group, which was E underline cross, and this was what makes appear geometrically the abelianization of the base. Okay, and I just finished with one example. First, one more remark maybe that therefore in this setting, I can also define and psi for 0 path lambda the at of the n not lambda, or maybe sorry, 25 n. Okay, I mean, once you have the Fourier transform, you just copy the definition I gave. You get similarly defined functors. So next lecture will be devoted to trying to see what these functors have to do with the Langlands pole.
So here you also need some relation between the duals of an I+1 thing or the ith term.
Yes,
yeah,
the
but
same
this
formal
all the same
applies as well. Yeah. Except that, yeah, the role of the dualizing sheaf is always just played as a super. So the condition that the slopes are non-negative is preserved. What's this operation? And just one example, and next time we will see more examples. If you take S filter and S sharp cemented, or yeah, I mean, or maybe just to make things simple, let me just, for simplicity, just take S to be the geometric point. Sharp is cemented. Zero perfect weak field containing E, tilting to C. Then, well, I told you that we have this Fourier transform for the skyscraper sheaf along this divisor, which is a functor from sheaves on for like affine line over this algebraically closed characteristic zero field lambda towards the same for the dual, but we computed the dual, it was again A1. C#. So, okay, it's for the diamond, but there is also an implicit claim that if you have like the diamond attached to some analytical space, then the category of attached sheaves are the same. So you get something which makes sense just in the usual rigid world, and it was in fact already studied by Hangaro from times ago. And what does it do, this functor? If you unravel the definition, you see that, well, the diagram, the Fourier transform diagram is just A1. Then you have A1 times A1 over C#. And first you use multiplication map to A1 again. And then you have this map in point mod E. Where does this map come from? Well, it just comes from the, so in other words, I claim that there is a, like, such a map is a datum of from E cross, sorry, so E underlying torsor over A1. And what is this torsor? Well, we already saw it. It comes from the fact that you have, well, it's given by the universal cover of the date G is take formal group law, one dimension and height 1 for P. So this is an E torsor over A1. This map is come from the logarithm of this take formal group. So this is what this Fourier transform is doing in this case. So it's quite reasonable that it is a Fourier transform, because like you pull back something. I mean, you define the kernel of this Fourier transform using this map, which is some form of the logarithm. So what you have is it's really like the usual Fourier transform where the kernel is some exponential function. So this is a bit surprising because a priori, if the algebraic world, this would be simply connected. Right? It's like a fine line about the characteristic zero base field, algebraic edges. But in this adic world, you have actually interesting eta covers. This was, as I said, observed by Ramiro, and it now appears as a special case of this more general construction. So next time, more examples on the relation to the expected relation to the Langlands correspondence.